So what do you have on the screen again this morning? Well, it's two waveforms, big deal. The bottom waveform, you may notice, is a step. The upper waveform is a triangle. I suspect many of you are already ahead of me. You're saying, oh, he's back to the curve tracer again. Yeah, that's true. What I've been doing is trying to find an inexpensive way to replace the analog discovery in the curve tracer circuit that I have previously shown, beginning with my number 179. Now, we'll take a look at one of those at the last video in this series before this one, although frankly the immediately preceding video about the XR function generator is related to this one. What you actually are seeing on the screen is that XR2206 function generator that I bought on eBay for less than $10. You can get them for kits for as little as $7 with free shipping, depending on how long you're willing to wait for them. I paid $10 to get it from an American distributor instead of waiting for something from China, but mainly that's just because I'm a little impatient. It was worth the extra $3. At any rate, low priced. And so what are we seeing? Well, what we're seeing here is a step generator that I built using a 7493 counter. You may notice that it has 16 steps. And it is synchronized to this triangle wave at the top. Now, both the triangle wave and the square wave that is driving this step generator come from the XR2206, and we'll talk more about that in a minute. But before we do, I just want to review for those who may not have followed the curve tracer. The purpose of this is to enable us to apply a stepped base current to a transistor, while we use a triangle to sweep the collector of that same transistor in order to display the characteristic curves. And for those of you that are kind of tired of this, the real purpose of this and the immediately preceding video were to see if I could replace the analog discovery at a low enough cost. And so what I'm going to do is assume that you already have an oscilloscope that has at least two channels and can at least do an XY trace. Then we're going to modify the curve tracer, particularly the use of the waveform generators from the analog discovery, and instead use that XR circuit that we've talked about. So let's do a quick review of how we got here, and then I'll show you more about this circuit. On the screen is my number 245 using a current mirror to further improve a curve tracer. And you'll notice on the left are the X and Y curves or traces, one of them being the collector voltage, the other being a representation of the collector current. In other words, a voltage which is proportional to the collector current. And then on the right, an XY presentation of these same waveforms showing a transistor being swept to collect its characteristics. So the step voltage that we just saw is to provide these steps that go up incrementally of the base current. The triangle wave is to produce a sweep of the collector voltage, starting at 0 and sweeping up to some value and then back down to 0. And for those of you who recall, one of the things that we discovered with the analog discovery was it didn't put out enough voltage to really test most small signal transistors. So we used a transformer to fix that. I won't go back into all of that detail. Look at the previous videos if you're interested or you didn't see them. So now let's go back and look at the circuit or circuits that we are using to generate the step signal, the step voltage, and the sweep current. Once again, these are the curves or the voltages that we are generating. I'm not going to talk much about this. This is a basic output from the XR generator, and if you want to watch the immediately preceding video on the XR generator, it talks about this. You have a choice of either a triangle wave or a sine wave. What I am going to talk about though is this step generator. So down on the bench is the XR2206, a little more light there. That's the unit on the left, and you may notice that I have I'm powering it off a 9-volt battery. Over on the right, I'm just using this project board to hold a resistor. I'll talk about why that's true in a minute. And then over to the right is the circuit that's of a little more interest. This circuit, which is a 7493 to set up to generate a step. It takes a square wave input into the clock. It then counts 16 times and then goes back to 0 and counts 16 again. Keeps doing that. Each of those 16 counts is being converted into a voltage by a set of resistors called an R2R network. And we'll talk a little about these, but more importantly, if you're interested in this more from a theoretical standpoint, I suggest a video by Alan W2AEW on the use of R2R networks. He has a really nice little graphical aid where he shows how you can actually construct those and how you can analyze them. I won't go into that. We're using this basically as a digital to analog converter. In other words, we're taking the digital signals being generated by this decade, or actually by 16 counter, and converting those 16 counts into 16 voltage levels. And those are the steps that you saw on the oscilloscope. So let's take a look at the circuit that we're using here. We've previously talked about the XR generator, and I'm just using the triangle wave out of it and the square wave out of it to create these signals. The square wave is being used to clock the 7493. So here is the circuit of the step generator. The basic circuit is a 7493. Now I chose a 93 rather than an LS93 because it provides more current output. You could go with an LS93, but if depending on how much base current you want to drive, and the step out comes up here, we'll talk about these resistors in a second, you want something that will provide sufficient current. Now you can use a low power device here, like a low power Schottky, but then I would suggest you might want to put some kind of current multiplier or an op amp, or maybe a emitter follower, resistor, transistor, whatever, on this step output. The easy way is just to use a 7493 because it has plenty of current output to not only provide for the resistor network, but also to provide sufficient base current to drive a transistor, at least a small signal transistor like the 3904. So what's all this about? Well, for those of you that haven't seen R2R networks before, they get their name from the fact that one of the resistors is a value R, in my case a 1K ohm, and another resistor is twice that, or 2R. So this is a 1R, this is a 2R, or R2R network. Now it's connected so that each of the outputs, this is the A, or least significant digit of the 7493, and each one is connected through a 2K resistor into this summing path. And what happens is when this point is high, it contributes current to this network. Similarly, when this is high, it contributes current to the network, and so on. That current is summed in a weighted manner. By that I mean the least significant digit gets the least weight, and the most significant digit gets the most weight. So, in other words, the current that you're getting out of the circuit, which is over here, is most heavily influenced by this digit, which is the most significant digit, less so by this, and so on. And each of these is influenced by a step of 2. So in other words, the weight of this is 8, this is 4, this is 2, and this is 1. The 7493 is simply being clocked by the square wave out of the function generator, and VCC is being supplied to pin 5, while pins 2, 3, and 10 are tied to ground. Now, by ground, I mean the ground on this board, because there's a quirk that I'll talk about in a second that causes me to have to offset the ground of the 7493 slightly due to a peculiarity of the XR generator. But the power supply actually is connected between this point, the negative, and this point. So 5 volts from here to here. The actual 7493 that I'm running is operating on about 4.3 or 4.4 volts. And that's simply because I'm using a fixed 5 volt supply here, and there's a 0.7 of a volt drop here, which causes this point to be about 0.7 of a volt above the power supply ground. Now, like I say, I'll explain that in a second when we talk about the XR. So the way that this whole circuit works is it counts up, starting at 0 and going up to 16, at which time it resets. It does need one feedback connection from pin 12 to pin 1, simply because when they designed the 7493, they wanted to allow designers the option of using this by 3 counter and this by 1 counter in different ways. I won't get into all of that. If you look at the 7493 data sheet, it'll explain what I'm talking about. So the way the circuit works is a clock comes in, the 7493 steps to a value. That value is then summed using these resistors to produce a step output. Then another clock comes along and the counter counts again. It starts at 0 and goes to 16, so there will be 16 steps. Now let's talk about this little peculiarity here, and then we'll wrap all this up. The XR2206 is in this case being run off a 9-volt battery, and one reason I wanted to do that is it causes this to simply float. In other words, there's no specific ground reference. I did that because I noticed that the square wave out from the generator, which is on this pin here, does not go all the way to ground. That's common. As many of you know, there are op amps, for example, that are called rail-to-rail, which you would think means that it goes all the way to the rail, but it doesn't. Nothing really goes all the way to the rail. The only way you can get a signal to go to the rail is to somehow provide some offset. Now that offset may be very small. In the case of the XR, that offset is a little over 0.5 volt. And the problem is a 7493 or any TTL circuit for that matter, does not work well with an output signal that only goes down to about 7/10 or 8/10 of a volt. It's not a sufficient zero. So what I've done is inserted a diode. It's actually right up there. You may or may not be able to see it. Here is the diode. Let me push it over a little bit. May be able to see it a little more clearly that way. That has the effect of raising the ground of the 7493 by 7/10 of a volt. So that is the purpose of the diode that you saw in the schematic down here. I would like to make a comment about this because it's one of those things that, quite frankly, in my mind, separates the really good engineers from the also-rans. And it is this. It's very, very important that when you are trying to solve a problem, that you actually concentrate on the problem, not on your first guess at how to fix it. Because a first guess at this might result in someone saying, oh, I need to build a level translator. Well, okay, but if you have a level translator, normally those are inverters, then you have to provide a second inversion. That introduces delay and causes the square wave that's clocking this counter, the step generator, to be out of phase with the triangle wave that you're trying to synchronize with. Admittedly, maybe by only a dozen or 2 dozen nanoseconds, maybe 50 nanoseconds difference. But nonetheless, it's one of those things that if you define the problem as this, the ground of this is too far away from the threshold voltage of the clock input, rather than in terms of how to fix it, then you can focus on simpler and more elegant solutions like this simple diode. Now, I'm not trying to teach a bunch of tricks here. What I am trying to do is to emphasize that one of the things that early in my career, I had a very good mentor who taught me the value of thinking clearly about the problem before you start thinking about the solution. Make sure you have the problem completely defined before, at least to the best of the instruments that you have and your knowledge of circuitry allows you to do it, before you set off trying to solve this. Because I can tell you lots of engineers would have solved this problem by some kind of level converter here and etc. When in fact all you really needed to do was offset the ground of the 7493 by about 1/2 a volt. I used a diode that puts about 7/10 of a volt, but since the clock only goes down to about 8/10 of a volt from ground, this effectively sees 1/10 of a volt as the 0, and then sees about 4.4 volts as the 1, which is well within the range of the 7493. So define the problem, then go look for a solution. Well, I hope that I'm not going to show you this in the curve tracer. I've shown the curve tracer so many times that it should be obvious to any of you that if you simply replace the waveform generator of the analog discovery in that curve tracer with this signal, and you simply replace the sweep signal with the signal that's shown on the oscilloscope there, that you will wind up with a curve tracer that has exactly the same characteristics. And because this is being generated by a very low cost $7 to $10 device that you can buy on the internet from dozens of vendors, That, combined with a 7493, a few resistors, and a diode, allows you to replace the analog Discovery 2 in that curve tracer. It also gives you a nice, not lab quality, but nonetheless useful function generator that allows you to vary amplitude and frequency. This is the coarse frequency, this is the fine, and this particular generator will go up to about a megahertz. Certainly not the equal of some of the nice function generators that I own, or perhaps you own, or you might have seen in the ads or in a lab. But for a hobbyist who's just looking for a quick way to build a curve tracer or some other circuit that requires waveforms, voltage waveforms, I think this is a neat little substitute for the waveform generator in the analog Discovery 2. And because it has outputs for both square and sine wave or triangle wave that are synchronized to each other, all sorts of applications spring to mind. Won't get into them here, but maybe in a future video. I thank you for watching this. I hope it's been informative. I hope it's shown you that you don't have to spend a lot of money in order to do some of these experiments. But more importantly, I hope it's shown you that if you clearly define a problem you're trying to solve before you go to solve it, you won't wind up trapped in the box. You hear people all the time talking about thinking outside the box, and that's exactly what they mean. Don't define the problem in terms of your first proposed solution. Define it in terms of the actual problem, and then you'll find the box gets a whole lot bigger. Okay, well, I hope you've enjoyed this series, and maybe at some point I can move on to something other than curve tracers. But in the meantime, I hope you'll have a nice day.